Hello and welcome back to everyone. My name is Shivam Agarwal and this is the second part of our brain tumor classification MRI project. Okay, in the last video we have saw the project's problem statement. In this we'll try to create the project from the scratch. Okay, so I'm using Kaggle community platform for creating this project. Kaggle supplies you with all the hardware and software requirements that you might want in your project. Okay, for example, if you want any amount of RAM, GPU or CPU, Kaggle provides you with all of those necessities. Also, you don't have to install any other dependency on Kaggle. Every library that we are going to use comes pre-installed with Kaggle. You can directly import and use those libraries. Okay, so I've already provided the link to this dataset and the notebook in the description down below. You can check over there. If you come over here, you will see the new notebook option. Before this, make sure that you have a verified, mobile verified Kaggle account, because then only you will have access to all the hardware and software functionalities that the Kaggle will provide. After doing that, you'll come over here and see this new notebook option. If you click over here, the Kaggle community platform will create a notebook for us, a Jupyter notebook for this dataset. Okay, so let us go and view over there. So this will be our notebook where we'll be executing our code. Okay, let us first name this notebook as brain tumor. Okay, so I'll be naming this as brain tumor. I'll be utilizing some GPU also because I will be training a neural network, and to train neural network you must use a GPU. Here I'll be using GPU P100. It is provided by Tesla. This GPU T4X2 is provided by Nvidia. Both of them have almost same performance. You can choose any one of them. I'll be choosing now for GPU P100. Okay, let us turn on the GPU. Let us start the session by executing the first cell. For executing the cell, you can use Ctrl plus Enter on Kaggle. So our session is starting. It is already imported NumPy and Pandas for me. Later on, let us import some more libraries. Okay. Let us start with nothing but Keras, because we will be dealing with deep learning. So let us start with Keras. It has imported the dataset also. Let us scroll down and import Keras for us. So K will be small over here. Then we have to import a model in Keras. Okay, so I'll say from Keras dot models. You already know what kind of model we are dealing with in deep learning is sequential. This sequential model will be common whether you create an artificial neural network or a convolutional neural network or a recurrent neural network. Okay, so we have imported sequential over here. Next we want to import some layers that we'll be having in a neural network. So whenever you create a neural network, you create an input layer where your input parameters will be supplied. There is an output layer which will tell what is the output of the processing, and between these two you have some hidden layers. Okay, so we have to create all those layers. So we first have to import them. So I'll say from keras.layers I will be importing some layers. The first one will be convolutional 2D layer, which is represented by con2D. This will be creating our neural network. Next is a flatten layer. So once you have created all the neural network, this will be dealing in a 2D matrix, but the output has to be a single number. So we have to convert that 2D matrix into a single 1D array. This layer flatten will be able to do this. Okay, so that's why we are importing it. The next will be a dense layer. You already know that dense layer is for processing. All the processing will happen in the dense layer. Okay. Next is a max pooling layer, which is represented by max pooling 2D. This max pooling layer works hand in hand with convolutional 2D layer. So whenever you have some convolutional 2D layer, it might happen that some of the features are preferred over the other. So we have to include them inside a pool. So that's why we use max pooling layer after every convolutional layer. Okay. Lastly, we can use a dropout layer as well, because we'll be dropping out some of the useless features or less relatable features after processing. Okay, so we'll be using dropout as well. Let us import that also. Finally, that we have imported our model and layers, what we want to import more is accuracy score, because we have to check how accurate our model will be after processing. Okay, so I'll say from sklearn. This sklearn is a machine learning library that you have already used in the previous projects. Inside this, I have something called as metrics, and inside it, I have accuracy score. So I'll say from sklearn.metrics import accuracy underscore score. Okay, so this will include all our required libraries for now. I'll say run, and it is imported quite quickly. Next, what we want to do is we want to see this data. So we have testing and training over here. Inside training, if you see, we have glioma tumor, meningioma tumor, no tumor, and pituitary tumor. These are the 4 categories that we want to visualize. Okay. So in the previous project, as you might have saw already, that we use something called as image data generator for our directory flow, or including all these images. Because we were dealing with just 2 categories, either cat or a dog, we were able to use the image data generator without any external input. Okay, but here we have 4 categories, so we cannot use image data generator. We will have to externally create a label. These 4 labels will be created, and all the files inside these labels are to be supplied inside a array. Okay, so we'll have to do all of this on our own. Image data generator cannot do this. So let us try to do this. For doing it, let us first import some of the libraries that are required. So I'll say import IPY widgets. So this will be required for our classification. Suppose I'll say as widgets. Okay, so IPY widgets is a library. I'm importing is that widgets. Next, I want IO, because this is the input output module. Okay, so I have to use some operating system based functions also. So I'm importing this IO. Next is PIL. So I'll say public image library. This PIL is called public image library. Okay, this is a library of Python. Inside this I have something called as image. So I'll be requiring this image also. Next, what I want is TQDM. This is a module, another module. I'll explain it to you later what it is. Then, as we are dealing with all these categories and we have to divide those categories, we will use something called as train test split also. Okay, so I'll say from sklearn dot model selection, we have to import a train test split. Okay, so this will do it. And lastly, to deal with images, we need something called as CV. So OpenCV is a library. In new Python versions, we have something called as CV2 in replacement of OpenCV. Okay, so we don't require OpenCV here. We can use CV2. Okay. Another library is Shuffle, because we are dealing with images and we have to use train test split. Train test split might not function better on these images. Okay, for shuffling these images. To shuffle these images into training and testing, we'll use something called as shuffle. Okay, so inside sklearn dot utils, inside the utils module, I have something called as shuffle. Okay, so I have this shuffle over here. And finally, to use all of this, I require TensorFlow. So I'll say TensorFlow as TF. Okay, so this will be all that we require for now. Let us execute this cell. It's saying sklearn.utils. Oh, this is from sklearn.utils. Okay, we have executed this cell. So that marks an end to our libraries. I know there are many libraries that you might have heard for the first time, but as we use them and as we use the functions inside them, you will get to know what they are used for. Okay, so now let us try to divide our data set into training and testing. So I'll say train test split. Okay, next on, let us create variables for train and test. So I'll say x underscore train will be an empty list for now, and y underscore train similarly will be an empty list. Okay. Next, we have to specify the image size. What size of the images we'll be using, because these images might be of different sizes. We have to scale them to the same size. So I'll be using something 150 maybe. Okay. Those images were not in large, so I'll be using just 150. Next, we have to define the labels. What are the labels? These four are the labels, these four categories. The labels our variable will mean the categories. So we already know what are the labels. Let me just copy it from here so I don't mistake it. So first is glioma tumor, and the next one is this meningioma. Let's just copy it. The third one will be no tumor. Let us copy that as well. And the final one would be pituitary tumor. Am I right? Yeah. So here is pituitary tumor. Let us copy this label as well. So we have our four labels for now. Let us move forward. So for each of these labels, what we have to do is we have to read all the images inside it, and we have to append them in train and test. Okay. So let us try to do it for each of these labels. So I'll use a for loop for maybe I in labels. This I will represent all these values one by one. So I'll say that path of this folder, because we are dealing with images, so we have to get the path. So I'll say folder path. The folder path to the first one in the label would be this training part. This training part will be the first one. So I'll say that folder path will be joined of os.path.join. This os.path.join function will join two paths to create a third part. So we are dealing with this training over here. We have this training path, and inside this training path we have four different paths. So one by one we will be joining each one of them and reading all the images inside it. Okay, so that is why we are doing this. So os.path.join, we have the first path as we have already copied, that is training, and then we have to add to it the ith path. Inside this training folder we are already present using this os.path.join. We have to append the label path for moving forward. Okay, so we have to copy this glioma tumor, but I have this inside the labels as I, so I'll mention I over here. So this folder path now will contain, in the first iteration it will contain the glioma tumor, in the second iteration it will contain the meningioma tumor, and so on. Okay, inside the training set. Next, what we want to do is, when we are inside each one of these, we have to read all the images. So we have to read all the images, so I'll use another loop. So I'll say for j in this directory, this particular directory. So to read a directory, we use something called as os.listdir function. If you have somehow used command prompt on our system, if you have used command prompt on Windows, you must have seen this listdir function already. This listdir function will list all the files that are present inside a folder. What is our folder? Our folder is folder path. Okay, so we have to list everything inside it. So we'll just supply the folder path to it. Okay, so this will be our folder path. As we have supplied it, now we have to read the images inside it. So to read images, I'll create a variable called as img. To read them, I will use cv. So I'll use cv2.imageRead function, imread. Okay, and then I have to specify the path. Now, how to specify the path? Remember that up to these four categories, we have path in folder path. We have to join the path of each of the images. So each of the image is represented by j, and the folder is represented by folder path. So we'll combine folder path with j. Okay, so that is how we will read it. And to join this path, we'll use again something called as os.path.join. os.path.join. Let us complete it. Yeah, so it is working right now as cv2.imread os path join folder path and j. We are joining for all the images. In this way we can read all the images. Now when we have read an image, we have to scale it. So to scale it, I will use something called as cv2.resize function. So this resize function is used to scale the image to the required size. Okay, extra indent is not allowed. So now I'll require the image that I have to resize first, image. Then I will require the parameters. Okay, what are the parameters? I've already said 150 over here, and that is stored inside the image size. So I'll supply the image size as well. And the image size will be always x comma y. So I'll supply it twice. So this will be the height and this will be the width of image. So I'll require 150 by 150, that is square images now. Okay, so that is how we'll do it. Next, now that we have read the image, we want to append this to the train. Okay, so I will say xtrain dot append function, and I will append the image to it. Simple as that. And what will be the ytrain value for this specific image? Because it belongs to a particular I inside the labels, so I'll say that ytrain will be the ith label. So the ytrain will be I, right? Or what you can do is directly just use categorical variables like 0, 1, 2, 3 for these four, and you can append ytrain as 0, 1, 2, 3. But I will do it later on. Right now I'll just append the labels itself. Okay, now that I have done this, I have to do this for testing as well. Now we have train variables, we want to get the test variables as well. Okay, so let us copy all of this. If I want copy, or let us just copy the loop. So I have to declare test variables, so I'll say xtest, or let's just ignore this xtest and xy. We have to what we can do is we can store all the training and testing images into the same folders, and then we can shuffle them and train our model on larger set of images. Okay, so I'll not split testing and training according to the user that has provided the dataset to me. I will include the training and testing both the images into training. Okay, and then we'll divide the training and testing according to our need. Okay, so let us just not create test variables right now. Let us just append all the training testing images also in the same testing folder. So I will say paste all of this. Now I have to join the training testing part. So I will replace just this training module by testing module. It is already replaced now, and now we are appending the same things to the xtrain and ytrain. What are these two loops are doing is we are taking the training images into the training variable, and we are taking the testing images into the training variable as well. Okay, then onwards we can divide the training variables into training and testing. Okay, because it might be possible that user has supplied us some values that are biased towards one in the testing and biased towards another feature in the training. So we'll use both the images inside training, and then we can split them according to our need. Okay, so after running this cell, what I'll be doing is I'll be having xtrain and ytrain with both the images, whether it is belong to testing or training. Okay, now as you can see, after this loop, the train variables xtrain and ytrain will be of a type a 1D array. Okay, so this 1D array is not required by our model. The array should be of type numpy array. Okay, so we have to convert the variables into numpy array. So I'll say xtrain equals np.array. np.array function will convert this into numpy type array. Okay, so I'll supply xtrain. So there's a lot of code that I have written inside this cell. I'm not sure if it will work in the first go, but yeah, you can always look up to the errors if they come. I'll say ytrain also. Xtrain and ytrain both will be stored like this. Okay. So I have this ytrain. Yeah, everything is looking good for me. Let us try to execute this cell. Okay. Just a bit mistake. We have to append this ytrain.append. When you have written so much code inside one cell, it is difficult to spot the errors also. So it is doing its task because it is dealing with a lot of images now, over 3000 or 4000 images. So it will take quite a few seconds to do, but I'm sure it will do it in this way. After this, what we'll do is we will shuffle all the images and we'll try to split them into training and testing. Okay, so we have to write code for shuffle, and that's why I have included this shuffle library over here. So as this cell is already executed, we have our training variables ready. Okay, now we have to shuffle those. So I'll say xtrain and ytrain. If now there is an important task here. If I shuffle xtrain and ytrain separately, then what will happen is they both values will be shuffled alternatively. However, I want a particular training value for x and y. Okay, so these are not to be altered separately. So we'll have to supply both the variables in the single statement. Remember, do not shuffle these two variables separately because that will alter our accuracy. Okay, so that is not what we want to do. We have to supply both of them in the same statement. I will say shuffle because we have already imported shuffle, so I think it will work right here. I have to supply xtrain and I have to supply ytrain. Okay, and I have to supply the random state. Yeah, over here the random state should be as high as possible. I'll keep the random state as maybe 100 or maybe 101. Okay, so this high random state will ensure that we have quite shuffled xtrain and ytrain possibly. Okay, and after this let us just see the shape xtrain dot shape so that we know how many images are there in training. Okay, so it is saying y, sorry, this is y underscore train. So now we have 3264 images, each of size 150 by 150, and each is having three channels, that is R, G and B. Okay, RGB channels are determined by these three. 150 by 150 is their size, and there are a total of 3264 images. That is the thing, that is the tuple that is supplied by this image property. Remember, this shape is not a function, this is a property of an object. Okay, that is why we haven't included parentheses after it. Now we are ready with our train test splitting. Okay, I might have already said it over here, train test split, but right now we were dealing just with the path and the folders of our program. So I'll say folder paths, and I think yeah, it is working fine. After this I will say train test split. Okay, let us try to split our dataset into training and testing. For that, you already know how to do this. I will have to get the train and test functions. I will require xtrain, I will require xtest, and I'll require ytrain, and I'll require the ytest function, ytest variable. Okay, these are the four things returned by the train test split. I will call train test split. Okay, that will require this training variables. However, the names might be confusing over here, so I will say x underscore train and y underscore train. These are the two variables required. Next is the test size. I will say that because the images are not large in number, there are 1000 images just in each category. I will say the test size is just 10% for now. You can vary this test size for experimenting, uh, but for now I'll say just 0.1 will be the test size. Finally, I have to give the random state. You already know why random state is used, and for now I'll give the random state as 101. Okay, this random state will ensure that the train test splitting is not biased towards one type of feature. Okay, that is how it will work. Let us execute this cell. Now we have our 4 variables, training and testing for x and y. Okay, now we are ready with creation of our neural network. But before that, you have to keep in mind that neural network has to deal with the numerical values, while in the training, y train values are labels. However, x train values are images converted to NumPy array, but y train are the labels. This glioma, meningioma, neotumor, and pituitary tumor. Okay, so we have to deal with the y train and y test values first. Okay, so we'll do it before anything else. I will say y train new. This y train new variable will be an empty list. I will say that this will store the values of the y train and y test. Okay, so I will say that for I in this y train, what I will do is I have to check whether it is belonging to which variable. Okay, so if I say that if it is glioma tumor, then the input will be 0. If it is meningioma, it will be 1. No tumor will represent 2, and pituitary tumor will represent 3. Remember what is common between what I told you and this list, that 0 is the index of this first label. 1 is the index of this second label. So we can directly replace all the values inside the list with their index. Okay, so we are just doing that. So I'll say y train new variable will append the index of this I. Okay, so this I will be belonging to labels. So I'll say labels dot index. This index function is used to return the index of that value inside that list. So labels is the list. Inside this, I have to return the index of I. Okay, so y train new will be the new y train value, and that is it. We'll just replace this y train with y train new so that we don't have to deal with this y train new variable. I'll say y underscore train equals y underscore train new. Okay, and similarly we'll do with test functions also. Okay, so now that we have replaced this, we have to convert this into categorical. I'll say that y train will be equals to tf dot keras. This tf is TensorFlow, keras is inside TensorFlow, and then we have something called as utils, and then inside this I have something called as toCategorical. I'm just doing all of this to convert the labels indexes into categorical variables so that our model doesn't give us an error. Okay, so I'll say y underscore train. So this will convert our y variable into categorical variables. This will be a small t to categorical. Yeah. Okay. Now we have to do the same thing for test also. I'll say the same thing, but for test this time. So it is y test. Inside y test we have and labels.index.I, the same thing, and for y test will be equals to y test new. We are doing the exactly same thing. This y will be small here above also, otherwise it will give us an error. And inside this we have test values. So we have the same thing for testing and training. Now that if we run it, we have y underscore train over here and not equals to. Let me scroll down a little bit. Yeah, so you can see over here inside y underscore train, and this will be underscore. Okay, and this looks fine. Yeah, let us try to execute it once more. Now we have our y underscore train and y underscore test as our categorical variables. Now we can use this x train, x test, y train and y test for creating our model now. Okay, so that is it for data manipulation. This was, I know, a longer type than the previous projects, but still we have done it in the correct way. Okay, this is one of the correct ways to deal with a lot of categories that we are having without imposing any bias. Okay, let us create a model quickly. Okay, you know already how to create models. So I will say convolutional neural network. Okay, it was not writing according to me. I want to say convolutional neural network. Putting a space beside it. Next, what we want to do is we want to create the model. So model has to be initialized as sequential. This sequential is common whether you are creating ANN, CNN or RNN. Next, we want to add some layers to the model. So we'll add our first layer using add function. Okay, so this is not the code value. This is our code function. Over here, if you can see, this add function will work as adding a layer. Okay, so our first layer will be convolutional 2D layer. So I'll say conv 2D. Inside it, I have to specify what type of layer it will be. So first we have to specify the parameters to it. So I'll be requiring 32 parameters to be trained on. Next, I'll be requiring a matrix for the padding. So the padding matrix may be of 3 cross 3. That will be enough for now. Next, we have activation. We require some activation. And for activation, I am using ReLU for all the layers other than the output layer. So I'll be using ReLU for the first layer also. Next, we want to specify something called as input shape. Okay, so this is the input shape that we require. Input shape, remember what we saw, it was 150. Okay, so we have to specify that 150 comma 150 comma 3. Why this 3? Because this is the channel. Okay, RGB channel. So we have to specify all of this. We can see over here we have our first layer. Next, again, let us add another convolution 2D layer. Model.add, and there will be another conv 2D layer. Let us specify the parameters also. Let us take 64 parameters now. Okay, these parameters will determine how many output units your layer will have. If it is taking any number of images, how many parameters it is going to process on and how many outputs it is going to preserve. Okay, so first layer had 32. Now we have 64. The padding will be same as 3. Okay, next we want to have some activation over here. So I am using activation for ReLU only. The activation will be ReLU in my case. So we have another convolution 2D layer over here. Let us add a max pooling layer because now we have to deal with the pool of values also. Okay, so I'll say model.add, and I'll be having a max pooling layer, max pooling 2D layer. Okay, because we are dealing with just 2D images, so I'm adding max pooling 2D layer. It can be of max pooling 2D and 3D according to the requirements. Inside this, I have to specify the pooling requirements. So I'll say that 2 cross 2 matrix will be good for pooling for now. Okay, let us add a dropout layer. If some features are not useful, I'll say dropout, and I have to specify how many features I'm going to deal with here. I'll say 30%. So I'll supply 0.3. This is how we'll create the convolutional 2D layers, max pooling and dropout. We have to create a larger network out of all these layers. Okay, so let us add some more convolutional 2D layers. I'll copy this layer over here. For quick responses, I will say paste and paste, but I will vary the parameters over here. So I am dealing with 64 over here. Let us deal with 64 for now. And the activation should be ReLU. Next, I want to add another dropout layer, and after that I'll add a max pooling layer. So this will be the dropout layer, and I want some max pooling also. So I'll say max pooling after this dropout layer. So we have convolutional max pooling, then dropout, then we have convolutional dropout and max pooling. So this is our current network. Let us expand it a little bit. We have another dropout after it. Let us add another dropout. So let us see. We want to have more convolutional 2D layers here because we have a lot of max pooling layers over there. So I'll say that I will copy this and I'll say paste it and paste it more. So we have a lot of convolutional 2D layers. Let us take 3 layers for now. But the parameters over here will be larger. Let us say 128 parameters over here. And all 3 I will say 128. Okay. The padding will be still 3.3,3. I don't need to change that. Let us add max pooling and dropout. So I have max pooling and dropout over here. Let us add one final layer of convolutional 2D layers. Okay. So I'll say 2 more convolutional 2D layers. But we have to create a lot of convolutional 2D layers for these 4 categories because we are having 4 categories. Let us say that I will change the second one to be 256 parameters. Okay. And I require the max pooling and dropout. So let us create another max pooling and dropout layer. So till now we have a lot of convolutional 2D layers. I think 9 convolutional 2D layers, and we have 4 max pooling and 4 dropout, or maybe 5 dropout. That is enough for the inner neural network. After this, what we'll do is we'll flatten it. Okay. So I'll say model dot add a flatten layer. Finally, that we have created the neural network, we'll go on to the output values. So I'll say first of all, let us flatten it. This will flatten the neural network output array. Then we'll add some dense layers for processing. The dense layer will require some parameters. Let us say 512 parameters it will be getting. And the activation would be ReLU because these are not the outer layers. So I'll supply ReLU only. Let us add some more dense layers. This time also I'll take the same layer. Next we want a dropout because we have processed some dense layer. So I want a dropout of all the useless features. 30% will be good. And finally I have the output layer. The output layer will be a dense layer. And inside it, the parameters is going to deal with are 4 in number. Why am I getting this 4? Because we have 4 categories. Okay, remember, whenever you have an output layer, you have to specify the units out of which you are dealing. Okay, we are dealing with 4 units, so we'll supply 4 parameters over here. So, and the activation, because we are dealing with either a yes or no for each of them, I'll say softmax. Okay, remember previously also I told you that when we are dealing on probability, we use softmax. If we were not dealing with probability, we would have used sigmoid. What is the probability here? Each type of image will be assigned some probability that yeah, this image belongs maybe 60% to one type of tumor, 20% to another type, 10% to another type, and 10% to no tumor. So that will be the case with our model. Whatever is the maximum probability, that will be assigned finally as the output of the image. Okay, so that is why we are using this softmax activation, because softmax deals on probability, right? So we have this neural network, a complete neural network. You can see a lot of layers are there. You can pause and see how many layers and how I have arranged all these layers. This algorithm is inspired from VGG16 model, where they use 16 convolutional neural network, convolutional 2D layers. Okay, let us try to execute this cell. It will take a bit seconds to create the model. So our model is now created. You can ignore all these warnings. Let us see the summary of the model. How many parameters we have and how many parameters we are going to train on. So let us see the summary using model.summary. Here is your summary. So we have 896 for convolutional first layer, then second layer we have 18,000 and it is going on increasing and increasing. Finally, we have total parameters as 4.4 million, which is quite good. Okay. In the dense layer, you can see 3.2 million are parameters for the first layer. So that is quite impressive. We have 4 outputs and we have all the trainable parameters. There is nothing that we cannot train on. Our model is looking quite good. Let us proceed with the training part. Okay. Before training, we have to compile this whole model inside one. Okay, we have to take it as a one unit. So we have to compile the model. I'll say model.compile. Okay, so we have to specify the loss inside it. Remember that we were using binary cross entropy loss because we were dealing with just two values. Here, as we have categories, so we'll be using categorical cross entropy. Okay, so we'll use categorical cross entropy. This loss will vary according to the model that you are creating. If it is just two categories, then we can use binary cross entropy. If it is more than two, then we can use categorical cross entropy. Then we have to specify the optimizer that we are going to use. Using optimizer, we will be using Adam optimizer for now. Adam will be good. Or if you have seen the last video, you can also use the best optimizers possible by importing this optimizer from the Python module. Okay. For now, we'll be using just the Adam optimizer. Next, we have to specify the metrics, but we are going to focus on mostly. So I am going to focus mostly on accuracy. You can focus on loss also. It is also a good measure, but for now, I will be focusing on accuracy. So let us compile this model with these values. Our model is compiled and is ready to be trained. Okay. So let us say history will be our variable that will store everything related to the training part. I'll say model.fit and I will supply the training and testing values now. So I have x underscore train if I'm not wrong, and I have y underscore train. Again, I think, yeah, this was the name of the variables. Next, what we want is the epochs. How many epochs will be there? So I think that this model will take a lot of time to train. So I'll supply just the 20 epochs. 20 will be good. I think the 20 epochs will not be able to give me a higher and higher accuracy, but for this scope, I think 20 will be good. You can train this model for 50 or 100 epochs if you want, but that will take a lot of time with GPU also. Next, what we want is validation split. So it will continuously run and train the model with different splits. So I'll say 0.1 will be good, 10% of the values. And that is it. I think that for now, that is it. I will fit the model according to these parameters only. Let us start the training. Oh, this is the first epoch that is going to be trained. Let us see how many parameters will be there. I think 80 parameters would be there. Yeah, there is 83. Okay, so this will take approximately 1 minute to train because we have 20 epochs. What you can see over here is for the first one we have loss as 2.4. The next one was 1.2. Then the loss decreases to 1.05. So we have decreasing the loss. It is already told that while dealing with deep learning models, we have to lower and lower the loss and increase the accuracy. So you can see the accuracy of the first epoch was just 29%. It increased to 41% in the next one and 53% in the third one. So you are seeing we already have got 87% accuracy in the 11th epoch only. However, I don't think it will hit the overfitting, because if it hits overfitting, then our model will not work properly. If the accuracy is too high, then also it is not good. Over here you can see we are using almost 85% of the GPU, which is 15.6 GB GPU. So 15.6 GB or 16 GB of GPU is not provided by any laptop manufacturer in the affordable range, right? So that's why I was using Kaggle Community Platform, as it provides me a large amount of GPU and CPU for this neural network processing. Okay, you can see over here our 20 epochs are done. You can see the loss is very low, 0.13 is the loss, and at the accuracy I hit 95%. this 95% is the accuracy on training data. Okay, now we will see how our model performs on the testing part also. Okay, our model was working quite good on training. For now, if you want to save this model for future use, so you don't have to just run the epochs again and again, what you can do is you can save this using model.save. Okay, so if you write brain tumor, okay, .h5 file, if you do this, you can see over here the saved model. For now, I will do the save for you to see how it is done. Next, what we want to do is we want to plot the accuracy and loss to see whether uh, the loss was decreasing in a proper fashion or not. So I will say that accuracy will be the variable and it will be supplied by the history.history. So the first history over here that you are seeing is the variable that model.fit was used with, and the second history is the function that we are going to call. Okay, inside this I have to write the accuracy because accuracy is something that we are going to deal with, and then we are going to deal with the validation accuracy as well. Validation accuracy. Okay, similarly I will write history.history of validation accuracy. Right, so this is how we'll get the accuracies. We have to plot them, so we will say with matplotlib, I will say that I don't think matplotlib is yet imported, so I'll import it, import matplotlib.pyplot as plt, and I will import cbond as SNS. Let us execute this cell. Yeah, so now they are imported. I'll say plt. First let us determine the size of the figure. Okay, so I'll say figure equals plt.figure. This is I am doing just to plot the image. Okay, so I'll say figure size would be maybe just 14 rows and 7 columns will be good. You can vary this according to your need. Then I'll say just plot it, plt.plot, and I will say plot the epochs first. Then I want accuracy and label as R. This label is R, you can remember it or try to copy it. Just don't go into deep what this means, because plt.plot function is just used to plot this accuracy and validation accuracy or losses. Okay, so I'll say that yeah, it is training accuracy because we have ACC over here. Similarly, we'll plot for validation accuracy as well. I'll just copy it. I'll say val ACC and I'll say validation accuracy. Okay, so now we have our plots for training and validation accuracy. Similarly, we can do for losses, but before that, let us do just a legend. And the location will be upper left. Okay, so location will be upper left. And we'll say plt.show. So this will show our graph. Okay, that is executed. Oh, so epochs is not defined. I will have to say the epochs, and this will be the range of values from length of accuracy. Okay, length of ACC. This has to be determined after accuracy, like here. So I'll say hit control enter, and it will draw the graph. Okay, so you can see I didn't do the different label over here. If I say B over here, and I've already saved the model, I don't need to run it. Okay, now you see that the training is red line and the validation is blue line. For both the things, the accuracy is continuously increasing in a good fashion. Okay, so we can visualize that accuracy was increasing. Similarly, we can do for losses as well. If I try to plot them, I will copy all of this. I will say loss, and I will say loss here. Validation loss. we just have to change the accuracy to loss, and it will be ready for losses as well. Let us execute it. Okay, so it is giving me, it is not giving me for loss, it is still giving me for accuracy. Also I have to supply here loss. Okay, so to visualize loss, you can see over here it should decrease in a continuous fashion. Yeah, so training and validation, both losses are decreasing, right? So if you write the same code for loss, you can see the loss is decreasing while the accuracy increases. So you can say that yeah, your model is working quite well now. Now the final part comes, that is prediction. So we'll say that prediction. Quickly let us try to predict the model better for our images. So quickly I'll say image equals cv2.imread. I'll be reading the image from this data and we'll be seeing if it is working fine. So I'll be loading the image inside it. I'll be supplying the path to it later on. Next I will say that img equals, we have to resize this image. So I'll say cv2.resize and I have to supply the size. The size that I have kept is 150, 150. Remember that. You can use img image size also over here as a variable. As I have already the image resized, I have to convert this to array because our model will require the array. Okay, oh sorry, equals np.array function of image. Okay, so this will convert the image to the array. Now we have to reshape this array according to our model. So finally I will say img underscore array will be equal to img array dot reshape. Because this is an numpy array, I can directly use reshape over here with a size of 1, 150, 150, 3. So it is already 150, 150. Okay, so we can use something called as image array reshape, or let us do that later on. Img underscore array dot shape. Let us visualize the shape of it first. Okay, okay, so I have to supply the image first. Inside the training module, let us say inside pituitary tumor, I have this 107 image. I am taking an image from pituitary tumor. Okay, let us execute it. So the size is, or the shape is 150, 153. Now what we have to do is we have to specify the reshaping. So I'll say img array equals img array dot reshape to the required value of 1, 150, 150, 3. Okay, so after this the img array would be reshaped. Let us just copy this and see if it is already reshaped. Now it is reshaped according to our model. Okay, next what we want to do is we want to predict it. So I'll say from TensorFlow dot keras dot preprocessing, I will import something called as image to visualize this image. Okay, so I'll say img equals this image is represented as small I. I will say image dot load image. Okay, this load image function will load the image. What is this image? I can visualize it over here. So this is the image that we require. Okay, it is loaded and we have to show this. So I'll say plt.imshow and the image that we have already loaded, and we have to specify the interpolation. I will keep it to nearest and I'll say plt.show. Okay, so this is our image that is of pituitary tumor. Okay, let us see if our model is predicting it or not in the right way. Remember that pituitary tumor stands for our label as 3. Okay, so I'll say a equals model dot predict for our img array. Okay, and let us see what is this a. First of all, a will be the probability array. So we'll have to take out the maximum probability index. So I will say that index, or index is a reserved word. I will say indices will be equal to a dot arg max. This arg max will return the index of the largest value, because the prediction will be the probability array. Okay, it will be an array of 4 numbers with 4 probabilities. We have to check what variable out of these 4 is the highest probability. Okay, so we will say that indices, and let us check what is the indices. I am expecting 3 and it is giving me 3. So you can say that 3 belongs to pituitary tumor, because 0 was glioma, 1 was meningioma, 2 was no tumor, and 3 was pituitary tumor. We are getting 3 over here. So this is how you will predict any image, whether it belongs to any tumor or not. You can utilize different images by specifying pass over here. Okay, so after this prediction, you will be able to analyze whether a patient MRI images show any sign of tumor or not. Okay, so that is how we'll do it. You have seen how to create the project, how to predict the images also. I think that this video was quite too long, but this was because we were dealing with a lot of images right here. I hope you have learned something good from this. Thank you for this series. You have learned machine learning models, you have learned deep learning with artificial neural network and convolutional neural network. Let us stop right there, and I hope that you will create more and more models over here on Kaggle also, and on your local machine also. That is it for this phase. Thank you.